So I ended my lecture yesterday without having time to take questions at the very end. So I want to start by asking if there are any questions from yesterday's talk that you didn't have a chance to ask then. It's not your last chance. Yeah.
So yesterday you said that it's pretty hard to get a explicit formula even for the bosons. So with this entanglement entropy machinery, will you be able to say something about that to this question?
Okay, so the question was about getting an explicit formula for the entanglement entropy for free bosons. So what I'm going to talk about today is using holography, and free boson is not a holographic theory. It's too simple. So it's not a case, so we won't be able to answer the question about free bosons using holography, but we'll be able to answer the question about strongly coupled large N theories using holography. Because those are, while from one point of view, from the point of view of sort of perturbative quantum field theory, those are complicated. From another point of view, they're simple in the sense that they admit this sort of thermodynamic description in terms of bulk gravity. So the question about free bosons in 2 dimensions remains an open problem. Yes?
You said when you separated the Hilbert space into the part corresponding to the example in A and its complement, this is kind of somehow an approximate separation.
Right.
How does that break down?
Right. Well, I think Edward answered that question, and also I think Ahmed kind of answered it, that if it truly factorized, then there would be states which are totally unentangled. But states which are totally unentangled basically don't exist in the Hilbert space of the field theory, and so therefore it can't be factorized. You know, one can. So I think I'll leave my answer to that. It's a very interesting question, and then that leads to the question: well, what is the correct? What should I replace that equation by, and so on? But since it's not really the topic of my lectures, and there'll be other lectures on entanglement and quantum field theory, I think I'll just leave it at that. I mean, I'll just say one other thing. If it makes you uncomfortable that we're kind of going on a premise which is false, one sort of simple way to think about the situation is that there's the actual Hilbert space, and then there's this sort of much larger unphysical Hilbert space which does factorize. And so any state in the actual physical Hilbert space can also be thought of as a state in this larger unphysical Hilbert space, because the first is embedded in the second, and therefore it has an entropy in that sense. Okay, I mean, one can give much more sophisticated, mathematically sophisticated answers to the question, but just that should at least maybe put you a little bit more at ease. Any other questions? Okay, so so the topic of today's talk is holographic entanglement entropy, but I realized there were 2 things that I wanted to say yesterday that I forgot to say about just entanglement entropies in quantum field theories. The first is that I promised an example of where the area law divergence is not the same as what condensed matter physicists call the area law. So the area law divergence is the statement that the leading divergent part of the entanglement entropy is proportional to the area of the entangling surface. And an example of that is a single interval in a CFT where the entangling surface consists of 2 points. So the area of the entangling surface is 2. And indeed, what is the divergent part here? It's 2 times c over 6 log 1 over epsilon. And so this is an example of the area law divergence at work. If I had 2 intervals, then I would have 4 here, and I would get 4 times c over 6 log 1 over epsilon. On the other hand, condensed matter physicists, in their terminology of area law, they would say this violates the area law, because the area law to them has nothing to do with the dependence on epsilon, but it's the dependence on L. and the dependence on L is logarithmic, whereas there should be no dependence on L, because what they mean by area law is S of A is like L to the number of space-time dimensions minus 2, which is how the area of the entangling surface depends on the overall size of the system. So in this case, it would be constant, but in fact, it's not constant. It's logarithmic. Okay, so just be aware of that. I mean, both are fine, just be aware of that distinction. Sometimes leads, in conversations, it sometimes leads to confusion. Okay, second thing is, I guess I never defined the term entanglement entropy. So let me just say, what does this phrase mean? It just means the entropy of a subsystem. It's not a good name, but it is the name we use. It's not a good name because it's not necessarily reflective of entanglement. Unless the full system is in a pure state, the entanglement entropy, S of A, the entropy of a subsystem, is not necessarily related to entanglement, or it may be partly related to entanglement, and so on. So it's a bad name, but it's the name we use. There's lots of bad names in physics that we just stick with. But on the other hand, sometimes you'll hear people who are trying to sound sophisticated claim that it's meaningless because it's just an entropy and we should just say entropy and not say entanglement entropy, which is like saying that the word subsystem is meaningless because any subsystem is a system, and any system can be considered as a subsystem of a larger system. So we should never use the word subsystem, we should only ever use the word system. So that's the same thing. When you hear somebody say we should never use the term entanglement entropy, we should just call it an entropy. It's exactly the same argument, okay? Okay. Okay, so that's the end of that. So now I want to switch gears back to where I was at the end of last lecture, which was trying to motivate Ryuta-Yanagi formula from an example where we know the answer. And the example where we know the answer, again, is a simple ADS black hole, static ADS black hole, eternal ADS black hole, that where the entropy is given to leading order in H bar by the Bekenstein-Hawking formula, which is the area of the horizon times 1 over 4 g Newton. And what we want to do is we want to, as I said, any subsystem can be considered any system can be considered a subsystem of a larger system. So we want to do that and interpret this as an entanglement entropy, this thermal entropy as an entanglement entropy, which we can do by virtue of purification. And the particular purification we want is the one that has a holographic dual. And the simplest one of those is the thermal field double, which I wrote down before, and also I think Ahmed wrote it down. And what is the holographic dual of that? Why, it's just the maximal analytic continuation extension of the short-chilled ADS short-chilled black hole, which has a Penrose diagram that looks like this. And so we acquire a new system, which I call A complement, which is just a copy of A. And where is the horizon in this picture? It's in this picture, it's the bifurcation surface where these future and past horizons meet each other. And if you just make a cut along a spatial slice, then this is what the geometry looks like. It's this Einstein-Rosen bridge. And the horizon is sitting here in the middle. And so we want to take inspiration from this and sort of generalize, say, well, what if I had something that wasn't just a black hole, and I had a spatial region, and I wanted to try to guess a formula for the entanglement entropy. So I have some bulk geometry, which I presume to be known. And let's just, for a little while, let's work on a time slice. So you know, it's, even though we're doing a relativistic field theory and we have this nice covariant, you know, bulk theory, general relativity, let's just kind of put that aside for a minute and work on a time slice. I don't want to keep this restriction forever, but let's just work on a time slice. And here, so let's just look at this picture instead of looking at this picture. What is it that's special in this picture about this red line? So, I mean, had we been working here, you could have said, well, it's the fixed point of the killing symmetry. But that presumes that I have this huge amount of symmetry, and maybe I'm in some situation where I don't have such a continuous family of isometries. And so, so what's the next answer? If you can't say it's a fixed point of some continuous family of symmetries, what's the next answer you might give about what's special about this this particular red line, or sphere in general? And I think the next best answer is, well, it's basically the minimal surface in this geometry between A and A complement. Okay? So it's the minimal area surface on the time slice that separates A from A complement. So then we're just going to guess that in general, so if, if we want to generalize this to some general space-time, then we'll have to work on a time slice. But there's many choices of time slice in general, so we're going to have to put some restriction if we want to kind of generalize a lesson like this. And the restriction we're going to make is, you know, if you ask, well, what's special about this? Why did I draw this time slice and not this time slice or this time slice? What's special about it is that it's invariant under a time reflection symmetry. Okay? On a time reflection symmetric slice, I like to use the word slice for spatial hypersurface, and surface for codimension 2 submanifold. So I'll try to be consistent in that way. So in general, for a region on a time reflection invariant slice, we're going to write this formula. Where M of A is the minimal surface. Let me give this a name. The minimal surface separating A and A complement on sigma. So let's say that instead of a picture like this, where A and A complement are disconnected manifolds, they're part of some common connected boundary, for example. An example like this. And so this is our bulk, which has some geometry asymptotically ADS. Well, since we're on a slice, so this is sigma. You want to look for the minimal area surface between that basically separates A from A complement. Okay, and this is basically the Ryu Takenagi formula. Now, there's a lot to be said about this. So maybe the first thing I'll say is that we're working in a semi-classical limit in the bulk. So we're working, if you want, effectively at small g Newton. And we already knew that in the black hole case, this was just the first term in an expansion, and there are corrections. And so again, we assume that there are corrections here. And there's a lot more to be said about those, but I'm not going to talk about those. Okay, so this is all in a semi-classical limit, and it's the first term in some expansion in g Newton. Okay. Second thing I want to say is, well, what does this mean? Between. So let me try to be a little bit more precise about the meaning of the word between. So what it means is that basically there's a part of the bulk of sigma, our slice, which interpolates between A and M of A. So in this case, here was M of A. And so there's some region here of sigma whose boundary has two parts. One is A and the other is M of A. And here, this thing would be here. Maybe I can actually just write it here. So, so between means there exists a region which I'll call R of A, which is part of the slice, whose boundary is the union of A and M of A. Now, if we're going to be a little bit more careful, it's useful to keep track of orientations. And if we keep track of orientations, like if we give A an orientation like this, so let's say we have one-dimensional, spatially one-dimensional boundary, and we orient A, then we would orient M of A like this, and then there's a minus sign here. It's not usually very necessary to keep track of orientations, but let me just try to be a little bit careful here. So this is M of A with reversed orientation. And what's handy is that this notion is already mathematically defined. So this is called homology. Okay, so we would write M of A, M of A is homologous to A. Okay, so here, and let me just be a little bit more explicit, I'm always working on sigma. So let me Okay, one other comment is that, of course, this assumption here is not too satisfactory in general because, of course, we want to be more general. We don't want to necessarily assume that our space-time has a time reflection symmetry, and even if it does, we don't want to assume that our region A lies on a fixed slice of that symmetry. So, for example, here, there's no reason, sorry, that's not a good example. In a case like this, where let's say this could just be ADS3, for example, the bulk could just be ADS3, and then the boundary is just a cylinder. If it was global ADS3, we would just have S1 times time. And of course, we could ask questions about a region A, which is on a constant time slice, but it's also very interesting to ask questions about an A which doesn't lie on a constant time slice, which is boosted somehow. And those are also interesting questions. And those are not covered, even though the bulk has a time reflection symmetry. If A doesn't lie on such a symmetric slice, then we can't use this formula. So my lecture on Thursday will be about how to relax that restriction. But nonetheless, so why am I even giving a whole lecture on this limited formula? Well, first of all, the generalized formula, which is the HRT formula, is much, 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 much harder to work with. And so if you can use this one, you should use this one. And so to get a good, get some good intuition about holographic entanglement entropy, it's sufficient to work just with this one, and that's why we prefer to do that. Okay? Okay. Another thing of terminology, right? This region here, because it defines the homology condition, we call it the homology region. Not a very inventive name. It plays an important role in a lot of the properties of and examples of entanglement entropies. And what you'll hear people talk about much more than the homology region is something called the entanglement wedge. And the entanglement wedge is the causal domain in the bulk of the homology region, okay, which is actually a wedge. So if you look at a case like this, so where we have, so we're working on some sigma, here's M of A, here's R of A, which is just on this slice, and then we can construct its causal domain, which indeed is a wedge. It's kind of in the neighborhood of the this minimal surface. It looks like a Rindler wedge, and that's called the entanglement wedge. And that's the causal domain of the homology region. But since I'm just going to be working on this slice sigma, today I'll just be talking about the homology region. Okay? Okay. Now, here we already see a new phenomenon that's not present in this canonical example we started with, which is that in this case, there's an entangling surface, whereas in this case there isn't. Here the region A was presumed to be one entire boundary, and so it doesn't have a boundary itself. And once we have an entangling surface, then we have a new phenomenon, which is that the homology region forces the minimal surface actually to meet the boundary on the entangling surface. So if you look at this equation, because the boundary of a boundary is trivial, that means that the boundary of A equals the boundary of M of A. And so that means that M of A has to meet the boundary of sigma on the entangling surface. Let me write that out. So this implies that dm of A, okay, and in particular, this implies that if dA is not empty, then M of A meets the boundary of sigma on the entangling surface. And so this immediately gives us some physical information. So let me draw, here's my, so let me give myself a little more space for this drawing. So let's look locally near the entangling surface, and let's say we have more dimensions than I drew there. So this is my boundary of sigma. So let me write that. So this is d sigma. And let's say this is A, and this is dA. So this is my entangling surface. Okay? And now here's my bulk down here. I like to draw the bulk below the boundary. So this is my z direction. Okay? And so what I'm saying is that just on topological grounds, the minimal surface is required, even, again, just purely on topological grounds, before we impose the minimality condition, it's coming up through sigma, and it must meet the boundary of the space on the entangling surface. But we can say something stronger. Because it's a minimal surface, it's minimizing its area, but it's got a problem trying to minimize its area, which is that the metric is going to infinity up here. So the metric is proportional to 1 over z squared. So it's forced to do something it doesn't want to do, which is to have a very large area. Okay? So the best it can do is to hang down vertically. Because if it hangs down at any other angle, if it meets the entangling surface at any other angle, it'll have an even larger area. And the most important thing is to minimize the area in the vicinity of the boundary here, which is where the metric is blowing up. Okay, so its first priority is to come off of the entangling surface vertically. And that is regardless of anything else about the geometry of A, the geometry of the bulk. As long as it's asymptotically ADS, which means you have this 1 over z squared factor, it's going to be coming down vertically. Okay, so it's going to look like this. And then what it does after that, of course, depends on the particular geometry. Okay? But we already learned from this, so we can already estimate a part of the area, right? So that means that the area okay, so let me actually write something. So for me, always d is the space-time dimension of the field theory, which also happens to equal the number of space dimensions of the bulk. And so this M of A is d minus 1 dimensional, and dA is d minus 2 dimensional. So here, when we calculate the area, we get a factor which is just, so this is just the part of the area from the part of M of A which is near the boundary. Okay, this part which is vertical. So we get a factor which is just proportional to the area on the boundary of dA. So I can be, so this is LADS. Let me just try to be consistent in my notation. I think I called this L. So this is LADS over z squared times the boundary metric. So when I calculate the area, I get a term, I get a factor which is from the boundary area of the entangling surface, which I call sigma, So this is the area of the entangling surface, times a z integral, integral from 0 up to something. So, you know, basically I'm only interested in this part of the integral, so I'm not going to put an upper bound on the integrand, on the range of integration, L over z, sorry. L over z to the power of d minus 2. Sorry. From the determinant of the metric. I should look at my notes more often. Okay, there we go. That's better. Okay, now, this is a divergent integral, but actually notice that the form of the divergence is the same as we had in this estimate of the entanglement entropy of Rindler space, right? So we have a divergence and we discover we have to cut it off. And so again, we have this UV divergence. Well, it's an IR divergence from a bulk point of view, but it reflects a UV divergence in the boundary, which we've cut off at some z equals epsilon. Okay? And so what you get is basically proportional, there's some factors, to sigma divided by epsilon to the d minus 2. So we get our area law UV divergence. So this is already the first great success of the Ryu-Takayanagi formula, because it has geometrically reproduced something we know happens in field theory, namely this area law UV divergence. Okay, this part is assuming d is greater than 2. Otherwise you get a log. But anyway, either way it's the same as we saw in field theory. And the way it does it is different. In some sense, it seems like different parts of this minimal surface are reflecting entanglement at different scales, which is at different scales in the field theory, which then add up to give this divergence, which is very natural because we're used to the idea that in holography, the part of the bulk which is deeper inside the bulk is reflecting more infrared physics in the field theory, and the part of the bulk closer to the boundary is reflecting more UV physics in the boundary field theory. And so here it's kind of working out very nicely. Okay? So what I'm going to do for the rest of the talk today is just go through all of the examples we did yesterday, but in this holographic setting, and see how all of the physics we saw in the entanglement entropy and field theories gets captured by the minimal surface geometrically, and also see some new things that we didn't see in the field theory. But let me stop for a second and see if there are any questions. Yeah?
That meaning for non-extremal surface.
Okay, the question is whether there's a meaning for non-extremal, non-minimal surfaces, and I guess we don't know is the best answer I can give to that. You could speculate, for example, here, yeah, let me just leave it at that. Yeah.
So when the minimal surfaces are not unique, you should pick the global.
This is, yeah, so, yeah. Okay, so the question was about global versus local minima, and actually thank you for asking that question. So here, yeah, in fact, I should have said, globally, and it's necessary to say this because mathematicians have a definition for the word minimal surface, which basically means what we might call locally minimal surface. It's their higher dimensional analog of the word geodesic. So a geodesic is not, as we learned at length in the previous lecture, is not necessarily a minimal length curve connecting two points. And so when mathematicians talk about minimal surfaces, they mean locally minimal. So they basically mean, I mean, you can say it in various ways, but they basically mean that each little bit, each little patch of the surface is minimal area if you pin down its boundaries. Or you can say it differently, that it has vanishing trace of the extrinsic curvature. And that's a weaker condition than what we mean here. We mean globally minimal. So if there's several locally minimal surfaces, you pick the one with the smallest area. So that's important. So if you ever discuss this thing with mathematicians, don't forget always to say globally minimal surface, or they'll get quite confused. Yeah?
When is the homology constraint supposed to hold? Because like in your picture above with the black hole background, the minimal surface encloses the horizon.
The minimum.
Disconnected from the boundary.
So here, the minimal surface is the horizon, and it's homologous to A by virtue of this region that interpolates between them. Now this, yeah.
When it hits the horizon, you try to like wrap it like a deforming to the boundary.
Say it again, would what?
If the surface wraps around the horizon, how are you supposed to deform it to the boundary so that it's homologous?
Okay, so the question was about deforming the surface. So I do want to emphasize that I'm not talking about a homotopy condition. So continuously deforming one surface into another is the mathematical notion of homotopy. I'm not using that notion here. I'm using the notion of homology, which is the existence of an interpolating region, lower codimension region. And they're not quite the same, although there is a relation between them. But so in this case, it does happen that the horizon is actually homotopic to the boundary. And in this case, it's also homotopic to the boundary. But we'll see a case later where it's homologous but not homotopic. But I don't know if I answered your question.
Well, I guess I was more asking, like, is the homology constraint equivalent to, like, the minimal surface always being anchored to the boundary?
Right. So, of course, here, so the question was about the minimal surface being anchored to the boundary. So the anchoring is a consequence of homology, but it's not, the implication doesn't go the other way. It's not sufficient for it to be anchored. It could be anchored and not homologous. It could be anchored on the entangling surface, but not homologous. So the homology is a stronger condition. And I'll show an example. Lest you doubt that it matters, why didn't I just say anchored? You can find examples. Basically, as long as you have some non-trivial topology going on in the bulk, then this will come into play. Yeah?
If you have, in the case where you have multiple locally minimal surfaces, but they all have infinite area, how do you distinguish which one is globally minimal?
Oh, that's a great question. So the question was, how do you distinguish locally, which locally minimal surface is the winner, is the globally minimal one if they all have infinite area? And the answer is you need to impose a cutoff. So it's only in the presence of a cutoff that question becomes well defined, and then you can ask the question of whether it's true that the answer didn't depend on which cutoff you chose. And the answer is that it can. I mean, you can, with sufficiently, that's actually a very subtle question that I don't have a snappy answer to, partly because I don't actually completely understand it myself. But if you allow yourself the freedom in making really wacky cutoff surfaces, so here my cutoff was just at a fixed value of z. then it won't depend on the value of epsilon, as long as epsilon is sufficiently small, which one is the globally minimal surface. If you allow yourself sufficiently wacky cutoff surfaces, then you can violate that, but probably those aren't allowed. So it's a good question. Yeah, Ahmed.
Is there a relation between wacky cutoffs in the bulk and wacky cutoffs on the boundary?
Well, yeah, I mean, this cutoff epsilon should be interpreted from the field theory point of view as the UV cutoff, right? So, but I could have a spatially dependent UV cutoff, which would be represented by some spatially dependent cutoff surface in the bulk. I don't know. People usually don't do that, so probably I just should not talk about it. Yeah.
Yeah, maybe just to follow up on this question. So, I mean, the bulk cutoff is different a priori to the CFT cutoff. So do you find a relation through RT, or is there like an independent way?
To relate this to the
CFT cutoff?
So, right, so the problem in trying to make the connection is that the actual numerical value you get for the coefficient of the area law divergence depends not just on the value of epsilon, but on the details of how you implemented the cutoff. And here I've done a very simple kind of brute force cutoff in the bulk, which is just to end the minimal surface at some z equals epsilon. And that doesn't really actually correspond to anything in particular in the field theory. I mean, that doesn't correspond to any of the cutoffs we would normally use just from a purely field theory point of view. So you actually can't directly compare them. There's probably a more sophisticated answer to that, but I don't think people have studied very hard the exact meaning of the cutoff in this context. I think. Right. So I was talking here about the coefficient here, and now in the log divergence, which we'll do in a second, the coefficient of the log is meaningful, but of course that one, being universal, doesn't depend on the details of how you implement the cutoff. Yeah.
Yeah, this is related to the previous questions, but the regular dependent parts of the entanglement entropy on the QFT side can be changed with different choices of counter terms for the field theory. I'm just wondering how to think of counter terms in field theory, I guess, in this geometric picture, or how it relates to the choice of the cutoff.
Right. So counter terms. Yeah, I actually don't know of a clean sort of way of relating so counter terms are used to make things like divergences in perturbation theory go away. And the precise connection between those and the divergences you get in entanglement entropy, I mean, yeah, maybe somebody else has a better answer to this, but what you can do with entanglement entropy is you can define a sort of renormalized quantities where you subtract off the divergent piece, and there's different ways to do that. So an example is, since we learned that the area law divergence is the same for every state, you could take the difference between S of A in one state, in some state, and S of A in the vacuum. And there, at least at a minimum, you should have gotten rid of the leading divergence. And in most cases, actually, you get rid of most divergences that way. And so that would be a sort of a renormalized quantity, which you can calculate also using Ryutake and Agi. So there are finite renormalized quantities. Another example is one we already did yesterday, which is the mutual information between separated regions, where the divergent pieces get canceled in the calculation of the mutual information. But in terms of the sort of conventional counter terms, and how those relate to the entanglement entropy, I actually don't have a good answer there.
The model you have a CFT, so right? So it's not, you don't have any more discount.
All these calculations
Well-
on CFT?
No, I mean, well, No, we're going to do a non-CFT example, but yeah. Yeah, I mean, when you do perturbation theory in n equals 4, you still, yeah.
Does this result depend on the fact that we didn't consider the higher order GN corrections? Like, if we take the higher order GN corrections, would this result change?
This result?
Yeah. Or like, how would
There would be another contribution. So even the higher order terms will have their own area law divergence as well. But that will be subleading in a different parameter, which is G Newton. Yeah.
Any kind of two different surfaces of exactly the same area.
Yeah, you can. We'll see an example. We'll see an example. Yeah.
So how would you like introduce excited states and like extra things in the CFT or in the boundary? What would it correspond to?
Right. Okay. So I have not. The only restrictions I've made for this formula are, first of all, we're in the semi-classical limit, and by that I mean not just that G Newton H bar is small, but also that the bulk, that there is a good description of the state as a solution to the classical Einstein equation. So I have a bulk geometry, which is a good description of the state. Okay? So that's one restriction, which was implicit in this. I didn't write it down. And the second is this time reflection symmetry. And I guess I should just, in that semi-classical, sorry, there is a third restriction, which I also didn't write down, which is that the bulk is governed by the Einstein equation. So we have Einstein gravity in the bulk, not some other theory like some higher spin theory or something like that. Okay? So I did not, sorry, I'm just remembering what your question is. I did not make any other restrictions on the state. So the state could be an excited state, it could be the ground state, it could contain a black hole, it could contain, so as long as it obeys this time reflection symmetry, it could have gravitational waves or any other stars and planets or whatever. So the idea with Ryu Takenagi, it's not just for calculating vacuum entanglement entropies. You can use the same formula to compute the entanglement entropy of a region in an excited state, as long as that state has a classical bulk description. Okay? And so what will happen if you're in an excited state is that the geometry here will be different. As a result, the minimal surface will be different. Its area will be different. A lot of questions. A lot of questions. Okay. Good. Okay, so probably it's helpful to see more examples. I think so. So, and actually, what I'm going to do in the example, so I'm going to stick to d equals 2, not just because of my limited drawing skills, but also because it's actually sufficient for a lot of what I want to show, and it's obviously simpler. So in d equals 2, m of a is a geodesic, and it's necessarily a minimal length geodesic. And so you can imagine, so here the bulk sigma is two-dimensional, and you're looking for a geodesic in a two-dimensional Riemannian space, okay, on a two-dimensional Riemannian manifold, which is not such a hard problem. At worst, you know, it's the kind of, it's in the class of problems that are, you know, Mathematica complete, meaning that you don't even have to know very much Mathematica to like have Mathematica solve this kind of ODE, right? And so I'm not gonna, actually the ones I'm gonna talk about are things you can just solve exactly with pencil and paper without even too much trouble, and I'm leaving that as exercises. I'm not gonna go through how you actually find the relevant geodesics, I'm just gonna state what they are, okay? And if you want to get a feeling for this subject, you need to do these exercises. They're all very doable, and it's quite educational. Okay, so the simplest one is an interval in the CFT vacuum. And so so CFT vacuum means the bulk is ADS3 global, or is and let's just say on a line. So here's, and then this thing has tons of symmetry, which makes it super easy to find the geodesic, and in the usual coordinates, so the spatial slice looks like this. So in these usual Poincare coordinates, the minimal surface is actually just a semicircle. You can see that it's homologous. And you can compute the length. And you reproduce that formula up there, which is a great triumph. Let's make it a little more interesting. Well, I'll just write it down. Oh, actually, I should say something else. Here, there's a relation. Yeah, how did we get C over 3? What is C here? Well, there's a relation between L G Newton and C. And so this thing, so the length, or the area, is proportional to little l. And in fact, it's twice little l times log big L over epsilon, and then you divide by 4g Newton, apply this, and you get C over 3. Okay? And this actually illustrates an important general feature that the entropies we derive from the Ryu-Takanagi formula are always going to be proportional to C, because they're always an area, which is really a length in d equals 2. And therefore, since the overall metric is proportional to LADS, when we divide that by G Newton, we're going to get a C. Okay? And then, as I said before, there's corrections, which are a power series expansion in G Newton, or if you want a power series expansion in 1 over C. Okay, let's do a more interesting case, which is finite temperature. So still on a line in a CFT. And now there's a nice simple formula for the metric. And you can, by the way, in the notes I sent out, all of these formulas are written down. So if you want to do the exercise that I suggested, you can find the necessary data, namely the metric, there. Now we have a horizon. So I'm assuming we have planar symmetry. You can also do it on a circle. Let's just do the planar case, because I want to take the limit of a large system size. So we have a horizon. Now, the metric up near the boundary is the same as that one. And so for a short interval, yeah. The area of M of A. Sorry about the handwriting. For a short interval, it's just going to be the same little semicircle. But when we make the interval longer, I'm going to do a whole family of them. The minimal surface starts to feel the horizon, and it looks like this. And what happens is it starts to hug the horizon. Now, we know that the horizon carries an entropy density, right, which is basically, well, which is its area divided by 4g Newton. Well, actually, more precisely, the entropy density in units of the boundary length is just the ratio of, is basically the redshift factor at the horizon which is so divided by 4g Newton. So it's basically the Bekenstein-Hawking entropy. It's basically just the length of the horizon divided by 4g Newton. And so here we see that because this minimal surface is hugging the horizon, there's going to be a contribution to S of A, which is proportional to the length of this interval times the entropy density, the thermal entropy density. Remember, we had a thermal entropy density, which I wrote down last time, for a CFT at temperature T. And when you now calculate the length of this geodesic as a function of L, you get the formula that I wrote down last time with the log sinh. But the more important, I mean, a better way to look at it is what I had before, where you have the part as a function of L, you have the logarithmically growing part, and then you have the linear part. And so, you know, what's exciting here is that, of course, you know, one thing is that we got the right answer, so that's very nice. But maybe what's more interesting is how we got the right answer, and in particular, how the minimal surface managed to reproduce the features here. Okay? And the way that it got, what's particularly interesting is the way that it got this linear piece is by having a part of the minimal surface which simply hugs the horizon. And so in some sense, you should think of this part of, roughly speaking, this can't be made precise, but if we sort of roughly speaking divide this long geodesic into this part and this part, the part which hugs, there's no precise way of making this separation, but just roughly speaking, the part which hugs the horizon is giving me this linear piece, and so that is reflecting the extensive entropy just from a volume law, right? And so each little piece of the minimal surface is either giving me that part of the entropy or the part of the entanglement entropy which is indeed due to entanglement between A and its complement. Okay? There's something else that's worth noting here that you might notice from this picture, which is that these minimal surfaces are nested. Okay? So as long as, so this region A is inside this one, and this one is inside this one, and then you see that this minimal surface is inside this one, and this minimal surface is inside this one. Or to state it a little bit more precisely, the homology regions are nested. And this is something you can prove. So if A is inside of A prime, then the region, the homology region for A is inside the homology region for A prime. Now, this is more than just a curiosity, because actually it's a great thing because it allows you, when finding a minimal surface, to ignore a large part of the space-time. For example, here, you notice that this geodesic never crossed the horizon. That's actually a special case of nesting, because I could have thought of this thermal state as being part of a thermal field double, could have purified it, included the other half, so then I would have had an A complement, not an A complement, but a complement for the whole boundary down here and so on. and then done the calculation again. Now, the entropy for A cannot know whether I purified this field theory, and if I purified it, how I purified it. It doesn't matter, right? And so it had better be the case that the minimal surface doesn't enter the region on the other side of the horizon, because if it entered the region on the other side of the horizon, then the answer we get would depend on what I put on the other side of the horizon, which is my choice. There are many ways to purify. Okay? So the nesting property actually gives us license to do the calculation just on one side of the horizon, as long as the question we're asking is only about regions of one copy of the field theory. Okay? So this nesting thing is actually implicit in what I did here. Okay? It's one of the things so in the last few years, people have taken this idea of the homology region and more generally the entanglement wedge, very seriously as a concept that has some important meaning in holographic dualities, the basic idea being that the entanglement wedge is the holographic dual of the causal domain of A on the boundary. I'll talk about that more on Thursday, but that idea that the entanglement wedge represents, so basically if you're asking about what's going on in some region A, you can just restrict yourself to, in the bulk, to its corresponding homology region. The only way that can make any sense is if you have nesting. Okay? This is a little theorem you can prove. I'm not going to go through the proof right now, but it's not too complicated. Yeah?
Great. So this expression that we found, this is, I guess, only valid for certain temperatures, because if it's ADS3, some people have a Hawking page transition.
So the question was about whether this is just valid for certain temperatures. So in this case, because we're on a line, the Hawking page temperature is 0. So this is valid for all temperatures. If we're on a circle, then indeed there would be a Hawking page transition at a finite temperature, and then we would have different behaviors on different sides of the transition.
Consider to disjoin and then we change the size of the interval, it will be like the nesting property will not hold, right?
No, it will hold.
But
So,
when you increase it, sometimes it will have a fixed transition, like the minimal
yeah.
sometimes become that.
Yeah, so I'll talk about that later. So, but nesting holds even in that case. The question was whether nesting holds when you have sort of multiple intervals. Yeah. Okay, and let me give one other CFT example, which is on a circle. And there, again, you get interesting qualitative features. And so now we have, and I'm back to the vacuum. And so now it's global ADS3. And it's not too hard again to find the geodesic. And to reproduce this thing that I plotted last time. So you get this log cinch. Log sine. Yeah, so what that looks like is like this, okay? Now, the interesting qualitative feature here is the fact that S of A equals S of A complement. Which had to be the case because we're in a pure state. And how does the Ryuta-Yanagi formula, I mean, in this case, if you just find the geodesic, calculate its length, you see it obeys this. But if you look at the picture, how did it know to make S of A equal to S of A complement? Well, look at A complement. Look for its geodesic. Well, it's sort of obvious that its geodesic is going to be the same. Okay, if I'm very careful with orientations, they're oppositely oriented, but they still have the same area. Okay? In this case, why does it happen that the minimal areas are the same? I mean, I think visually it's sort of obvious. The minimal surface for A complement is not going to go somewhere else because basically you're solving the same geodesic with the same boundary conditions. Okay? A little bit more formally, any surface which is homologous to A, or let me say it this way, A is itself homologous to A complement. Why? Because the union is the boundary of sigma. Therefore, any surface which is homologous to A is homologous to A complement. So when you're applying the Ryuta-Yanagi formula, you're minimizing the area over all homologous surfaces. You're minimizing over the same set. So you're going to get the same minimum. Okay? Now, you could say, well, wait a minute. You can't say that Ryuta-Yanagi always predicts this situation. Because this is not always true. This is true, this is always true if the full system is in a pure state. But if the full system is not in a pure state, this is not necessarily true. So the argument I just gave must break down if the full system is not in a pure state. So let's study that example a little bit. But let me actually first say one quick thing, which is that all of the examples I've shown you so far are total cheats. Because secretly, by a change of coordinates, they're all just black holes. So the only thing I've proven to you is that we've reproduced the Bekenstein-Hawking entropy. It's just some black hole and some funny coordinate system. But that wasn't the point. The point was the qualitative features, and I'm sure you can imagine that if we were in higher dimensions, if we had some more complicated geometry, and we didn't have all these symmetries, because in 2 dimensions, everything is so simple, and you have such a large conformal group, then the qualitative features would still go through. So I use these as illustrations, but if you're being very careful about whether or not I have provided evidence for Ryuta-Yanagi by doing these checks. In fact, they don't provide any evidence themselves because they're all just Bekenstein-Hawking entropy. Okay. Yes?
Do you have an example where this minus sign comes important in some context? The orientation minus sign?
Yeah, I'll give one. Okay, so it was a great triumph that Ryuta-Yanagi predicted this important property of entropies in pure states. And I gave that argument. That's important enough, let me actually write it. So this implies that if M is homologous to A, then M is homologous to A complement. I'm not putting the signs in here. So here we have a minimization over the same set of surfaces, if you can read that. Okay, which implies, I left off the punchline, implies S of A equals S of A complement. But what I was saying was that if Ryu Takenagi predicts that this is always the case, then we're in trouble, because we know it's only necessarily the case in a pure state. So what happens if you're not in a pure state? And this is where the homology condition becomes crucial. So let's give an example of a non-pure state. Well, we did one here, and I could have actually already done this example, but it's a little confusing because you have an infrared divergence for A complement. So I just basically want to do an example like that, but in finite volume. So thermal state above the Hawking page temperature on a circle, and we have a horizon now. So we have some BTZ black hole, let's say, for in 2 dimensions. And now we have A, and we have A complement. And now we go looking for the minimal surfaces, the respective minimal surfaces. And basically, even before doing that, we see it's just not true anymore that A is homologous to A complement. So the argument has broken down at the first step, because even though there is a time slice sigma, it is not true. So this came from the fact that D sigma equals A union A complement. And this is already not true, because here we have D sigma is A union A complement union the horizon. By the way, I didn't say that if you're in a mixed state, then this has to fail. So certainly there are cases where you're in a mixed state and yet S of A is equal to S of A complement. And so if I had been in a thermal state below the Hawking page temperature, there would have been no horizon, and that argument would have gone through. Although it turns out it would only have gone through at leading order. Then you have to look at the subleading corrections in G Newton, and it actually would have failed there. But you wouldn't see that if you were just using Ryu Takenagi. But anyway, here it's thermal enough. In other words, we're in such a mixed state that you start to see the difference at leading order between S of A and S of A complement. So the argument is broken down, but what is actually happening with these minimal surfaces? I mean, is it just because the argument broke down doesn't mean the conclusion is wrong? Well, let's look for them. Well, for A, you're going to get typically something like this, if A is relatively small. In this picture I've drawn, A complement is much larger. It's larger than half the size. And so what is its minimal surface going to do? Well, its minimal surface has to be homologous to A complement, and this is not homologous to A complement. Because if I pick a region in here, the boundary of that region includes not just this M of A, but also the horizon. Okay? Now, the minimal surface, so the union of M of A and the horizon is a locally minimal surface because the horizon is minimal and M of A, of course, is minimal. And their union is homologous to A complement. There's another locally minimal surface which is also homologous to A complement, which goes around like this. It skirts the horizon, doesn't actually coincide, although I drew it like that. And this one is also homologous, so I could call this M2. And so you just have to calculate, and actually it depends on the details of the geometry and your sizes and so on. In some cases, this will be globally minimal. In some cases, this will be globally minimal. But in any case, the homology condition has done its job by making sure that M of A is not homologous, is not in the class over which we're minimizing for A complement. And so you will find in general in this case, S of A is not equal to S of A complement.
But what if I think of it as a thermalizing pure state? Then the entire
Where is the question coming from? Oh, sorry.
So what if I think of the state as a thermalizing pure state? Then you also have a black hole, but it is a pure state.
Ah, great question. So the question was, why don't you just purify this? And then this will be true. And so I can purify it by going to the thermal field double, but now I have a different A complement.
No, the question was
Oh,
black hole.
oh, sorry.
Pure state, like it's a black hole that is.
Oh, that's not in the class I'm considering because that's not a semi-classical state.
Why not? It is. It comes from collapse, right?
Oh, sorry, I thought you were talking about a static pure state black hole. From collapse. Ah, good. So that one, see, I always have an answer. So that one does not have it's dynamical, does not have a time reflection symmetry. So for that you need to do the covariant formula, which we'll do on Thursday. And in that one, it turns out you do find, in a collapse situation, S of A equals S of A complement when you apply the covariant formula. So clever how it manages to...
So if when the state below the temperature below the phase transition, what's the argument for the field theory side, the leading order, they have the same entity?
The Araki-Lieb inequality. Oh, the question was, what's the argument from the field theory side that if you're below the Hawking page transition, then at leading order they would have the same entropy. So Araki-Lieb tells you this. And this is, or in that case, the total thermal entropy is order 1, or let me be more explicit, order G Newton to the 0. Does that answer the question? Okay. Let me go on to the next example, which is not a CFT, which is a gapped theory. And so first of all, what does a holographic gap theory look like? Well, basically it looks like one where the z direction ends. So there's some kind of wall, even in the vacuum. So it's not that there's a horizon. Even in the ground state, the z direction is just capped off by some kind of wall. And there's a lot of ways to do that. And a lot of ways to model confining gauge theories holographically that way. And I'm not going to go into that. I'm just going to use this most boneheaded model of a gap theory, which is where I just declare, without explaining why, that the z direction has ended at some value of z. So we just have a wall here. To make it sound fancy, I'll call it a confining wall at z. It turns out the value of z where you want to put the wall is the correlation length, meaning that if you take this model, so in here I just have an ADS metric, okay? And then if you compute, let's say, 2-point functions in this background, you'll find that they die off exponentially with an exponent which is given by the value of z where you put the wall. So that justifies calling it the correlation length, okay? This is not an actual solution to gravity or to string theory, but there are actual solutions to string theory and even to higher dimensional gravity that basically look like this or close enough. So an example that's commonly used is, so of course there are secretly extra dimensions here often in many holographic theories, which we haven't mentioned. Those extra dimensions can smoothly cap off so that the full higher dimensional space is smooth, but from a lower dimensional point of view, it looks like space just ended here. Things like that you can do, okay? What happens when we apply Ryuta-Yanagi here? It looks kind of similar to the thermal case, but there's a very important difference. So let's say we have a small interval. Oh, sorry, before we do the interval, let's just do the half line. Well, let me first say, actually, I won't draw it, but there's an even more trivial example, which is to take the full thing, right? Just make A the whole space. Now, I told you this was the ground state of my putative theory, and so it has no entropy. And that means that it's not like in that case, where if I'd taken the full thing, I would have taken the full horizon as my minimal surface. You don't want to take this wall as your minimal surface, because then you would get a non-zero entropy, okay? Actually, what happens in a lot of these models where the extra dimensions cap off smoothly is that the Einstein frame metric in the lower dimensions actually goes to 0 here. So even if you did take this, you would get 0. But let's say it doesn't do that. Let's say we actually have a non-zero metric on this wall. This wall is not a horizon. It does not carry entropy. So we better change the rules of the game if we want to get the right answer. And the way to change the rules of the game is simply to modify the homology condition so that basically the wall doesn't count. So in other words, this equation where'd it go? The definition of homology oh, there it is. There exists a region, yeah, here. You give yourself a fudge factor, which is this equation only needs to hold modulo this surface. Okay? And that, if you want to sound fancy, that has that's actually a well-studied kind of homology in mathematics called relative homology. So we're doing homology relative to the wall.
That means any portion of the wall doesn't count.
Any portion. Doesn't have to be the whole thing. Exactly. Great. And so this frees us now. Let's get back to the half line. And you want the minimal surface. It's going to have to end on this entangling surface, so it's going to be a geodesic, but you don't want it to end anywhere else. So it's just got to end on the wall, and here's my homology region. And what do we get for the entropy? Well, just integrate. This one is easy. You integrate 1 over z dz from xi to epsilon. So S of A is 1 over 4 g Newton. Integral from epsilon to xi dz L over z, because I told you that the metric in my boneheaded toy model is just the ADS metric between here and here. Of course, you can do this calculation in a more interesting model. But we get C over 6 log C over epsilon. Once you use that formula there for L over G Newton is 2/3 C, which is what we got before for Rindler space. Now, of course, you might say, oh, it's amazing you didn't get any finite part, but of course that's because this was like a very overly simple example. In a more realistic example, you would get a finite part and so on. So don't take that too seriously, okay? But in terms of the dependence on C, first the dependence on epsilon we already knew from the discussion before, but in terms of the dependence on C, that comes out because of this geometry, okay? Yeah?
And there are some field theory on the wall, so that will give you all the Y contribution to your answer.
That would give you what?
All the Y contribution.
I think you could consider some, so the question was if you have a field theory on the wall, would you get an order 1 contribution to the entropy? There are probably models, yeah, I think there are certainly models, I mean, we could have all kinds of interesting brains in here that have field theories living on them and stuff like that, and then you would have to include that in the order 1 stuff, but I'm not talking about the order 1 stuff, so, yeah.
Maybe you can comment that this condition that it doesn't count in homology and so on, you can derive it from the higher dimensional examples. Right?
Good. Right. So, right. That's a good point. So, in the case where this wall comes from a smooth capping off of a higher dimensional geometry, of the extra dimensions in a smooth higher dimensional geometry, then we could just decide to work in higher dimensions from the get-go, apply Ryu Takenagi there, and then this isn't a boundary at all. There's no, from a higher dimensional point of view, there's no boundary here in the first place. And so this is something we derive from Ryu Takenagi. Yeah?
I think with the GT bar information is the boundary side of the bulk set, this construction suggests that the entanglement is finite.
Okay, the question is about entanglement entropy after you do the TT bar deformation, which I think is a great question that I absolutely haven't thought about. I mean, that would seem to make the prediction that you get finite entropies. I certainly haven't thought about it. If no one has done it, then you should quickly write a paper on it. So I just wanted to do, the last thing before we end, I wanted to do an interval in the gap theory. I guess I have this space here, right? Because that also brings a new qualitative feature, which is something we didn't see in the field theory case. So here's my wall. Again, as we've seen a couple of times already, for small intervals, the geodesic doesn't notice the wall, and on the other hand, for a long interval, longer than Xi, when you look for the minimal surface, there's no geodesic actually in this space that connects these 2 points. So what you have to do is you have to go to the wall, and actually there's an intermediate regime where there are 2 choices. You can either connect them by a geodesic or just go straight down to the wall, and then at some point there's a switch from one to the other. So what the entropy looks like as a function of L is at a length Xi, it switches from the logarithmic to an exactly constant value, which is just, that constant is just twice what we had over there. It's just the C over 3 log C over epsilon. Okay, so this is qualitatively, if you remember, I drew a plot yesterday for a gap theory which was qualitatively like this, but I drew it smoothly. And yet here we see what appears to be a phase transition. We have a switch, and there was a question before about whether two minimal surfaces, locally minimal surfaces, could have the same area. And at this point, they have the same area. One locally minimal surface is doing like this, and the other is doing like this. And at this point, they have equal area. This is not something you would expect normally in a field theory. It looks like a first order phase transition. And you could even object that it's impossible. Because, let me give the argument of why we would expect in a field theory this actually to be a smooth curve. The argument is that once you have the cutoff and you have a finite length interval, you have a finite number of degrees of freedom, and in a system with a finite number of degrees, there was another step in the argument. So what I can do is I can consider this state, rho sub A, to be a thermal state with respect to the modular Hamiltonian. And all I've done in changing the length of the interval is change the parameters in the modular Hamiltonian. So I have some one parameter family of modular Hamiltonians, and I'm looking at the thermal state. I have a system with a finite number of degrees of freedom. There can't be a phase transition. Okay? So we expect all of these entanglement entropies as a function, when you continuously vary parameters, to always give nice smooth functions, okay, as functions of the parameters like the length of intervals and so on. But here it's not smooth. Well, the answer is that we know that there can be phase transitions even in finite volume in holographic theories. There's one mentioned right here, which is the Hawking-Page transition, which occurs even in finite volume holographically, because holography is a thermodynamic limit, just not an infinite volume limit, but one where instead you have an infinite density of degrees of freedom because you're taking like some type of large N or large C limit. So the existence of a phase transition, just like the Hawking-Page transition, is due to the fact that we're in a theory which has a large number of degrees of freedom per point. And that shows, in fact, that, and I'll end with this, that there must be corrections that smooth this out. There must be 1 over C corrections, or if you want, G Newton corrections that smooth this out. We know something about what those corrections look like for the Hawking-Page transition when you use Euclidean quantum gravity and you have competing saddles. And then you can estimate the non-perturbative. The smoothing out is due to non-perturbative corrections. Smoothing out of phase transitions is never due to perturbative corrections. Perturbative corrections can never smooth out a phase transition. It's always non-perturbative corrections. And so, so let me just write this. At finite C, it must be smooth. So that means that it's smoothed out by non-perturbative corrections. And what's interesting here is that unlike the perturbative corrections, which I've alluded to a couple times, the order 1 stuff, which is pretty well understood, and unlike the Hawking-Page transition, where the non-perturbative corrections are somewhat understood, the non-perturbative corrections to Ryu Takenagi are not understood. This is an important an opportunity for you to answer an important question, which is what do the non-perturbative corrections to Ryu Takenagi look like? How do they actually, can you estimate how they smooth out this phase transition? Okay, I'll leave it at that. Questions or no? No questions.